Now that we've gotten comfortable with the definition of the derivative, the common frustration is how tedious that formula is. So the question that starts to come up is, what are some derivative shortcuts? So that we don't have to go through that formula every time. And you can imagine as a function becomes very complicated, the derivative function could become very tedious to work through. Well, there's lots of derivative shortcuts we're going to look at over the next several lessons. We're going to look today at 4 basic shortcuts. And then after that, we'll take a look at 2 important shortcuts that are a little bit more involved. The most basic is the constant shortcut. And the idea of the constant shortcut is if we take the derivative, d dx is the alternative notation for a derivative, the derivative of some constant or some number, we're going to always get 0 for our answer. Because if a constant is a straight line, the derivative of a straight flat line is 0. So for example, if I wanted to calculate the derivative of 5, a constant, well, that's just going to be 0 because 5 is not changing. It has a slope of 0. The second basic shortcut is the power rule, and this is probably the one we will use the most. And the idea is if we're taking the derivative of x raised to some exponent. When we have x raised to some exponent, we'll pull that exponent out in front, and then we will reduce the exponent by 1. And this is probably the most used derivative shortcut. With polynomials, we pull the exponent out front and then decrease the exponent by 1. So for example, if I wanted the derivative of x to the 7th power, all I have to do is I move that 7th power out front, and then I reduce the exponent by 1, and we get 7x to the 6th. A third rule, I'm going to call it the sum rule. It's often called the difference rule as well because it works with plus or minus. And the idea is if I take the derivative of some function plus or minus another function, where I know the derivative of the individual pieces, all I have to do is take the derivative of the individual pieces. And it's f prime plus g prime of x. So for example, combining the power rule and the sum rule together, it should be plus or minus. If I wanted the derivative of x to the 5th minus x squared plus x plus 2, we just take the derivatives of the individual pieces. The power rule says we move the exponent out front and subtract 1. So we get 5x to the 4th minus x squared, bring the 2 out front, subtract 1 from the exponent, we just have x, plus, with x, that's really x to the 1st, so we pull the 1 out front and drop it by 1. So x to the 0 is just 1. And then the derivative of 2, a constant, is just 0. So all that we're left with is the 5x to the 4th minus 2x plus 1. The final basic shortcut is the constant multiplier. Which says if I'm taking the derivative of some constant times a function, we keep that constant in front and multiply it by the derivative of that inside function. And that is the 4th basic shortcut. So, for example, if I wanted the derivative now of 3x to the fifth minus 2x to the fourth plus 5x squared minus 7x plus 1. Let's get us a little more whiteboard space so we can put it right underneath it. The 3 can just be multiplied by whatever the derivative is of x to the fifth. Well, we know we pull that exponent out front, so 3 times 5 is 15. X to the 1 less, fourth power, minus, bringing the exponent out front, 2 times 4 is 8. X cubed, shrinking the exponent by 1, plus 2 times 5 is 10. X, shrinking the exponent by 1, minus 7 times 1 is 7. Shrink the exponent by 1 and the x disappears, and the derivative of the constant is 0. So now we have our new derivative of that polynomial. These 4 basic rules of differentiation will save us a lot of work and time on that derivative formula. Now, in fact, we should be able to quite quickly find, let's do this in black, quite quickly find the equation of the tangent line to f of x equals 4x cubed minus 2x squared plus 5x minus 1 at x equals -1. Well, first we need to know what the y-coordinate is that we're going to end up with. Actually, no, first let's actually find the derivative at 1. So first we're going to take the derivative, f prime of x is equal to 4 times 3 is 12, x squared, subtract 1 from the exponent, minus 2 times 2 is 4, x, plus 5, and the x disappears. We want it at specifically x equals -1, so we'll do f prime of -1, which is 12 times -1 squared, minus 4 times -1 plus 5. And if we work that out, it becomes 12 plus 4 plus 5 is 21. So the slope we now know is 21. We do need to know the y-coordinate of this point. When x is 1, what does y equal? So we do need to plug the -1 into the original function as well. F of -1 is equal to 4 times -1 cubed minus 2 times -1 squared plus 5 times -1 minus 1. So our y-coordinate is equal to -4 plus 2 minus 5 minus 1, which gives us -12. So for the equation of our line, y equals the slope we found out was 21 times x minus x1, minus a -1 is +1, minus 12, and our line tangent to our function is 21 times x plus 1 minus 12. So those are our basic properties to help with differentiation. The next two are a little more involved, and they take a bit of practice to get used to using. We'll see a lot of errors with this one particularly, which is the product rule. The product rule says that the derivative of two pieces that are multiplied by each other, f of x times g of x. The common error I see is people just take the derivative of both and multiply, and they say f prime times g prime. That is incorrect, and it does not work. What we actually do is the derivative of the first part times the second part plus the derivative of the second part times the first part. So there's two parts to it, and we take the derivative of the first part in the first part, and the derivative of the second part in the second part. So for example, if I wanted to take the derivative of 3x squared minus 5x plus 1 times 2x squared plus 4x minus 7, we've got two individual parts. So the formula says we take the derivative of the first part. The first part, the 3x squared, let's color code these. We'll do the first part in blue and the second part in green, just so we can see how this works out. So in blue, the derivative of the first part is 6x minus 5. Then that is multiplied by the second part, 2x squared plus 4x minus 7. Plus, then we take the derivative of the second part. The derivative of the second part is 4x plus 4 times the second part, 3x squared minus 5x plus 1. And this, then, as ugly as it looks, is the correct answer for the derivative of that product. So the derivative of the first times the second plus the derivative of the second times the first. Let's look at one more. Let's do the derivative of 5 over x squared plus 3 over x times 2x cubed minus 7. Whoa, we don't really have a derivative trick for x's being in the denominator. Actually, we do. We just need to tweak this problem a little bit and rewrite it as the derivative of, and think about what type of exponent sticks things in the denominator. Well, a negative exponent does that. This is really 5x to the negative 2 plus 3x to the negative 1 times the 2x cubed minus 7. So again, now we're multiplying two polynomials, a first part times a second part. And the formula says it's equal to the derivative of the first. 5 times negative 2 is negative 10x. And if we subtract 1 from negative 2, the new exponent is negative 3. 3 times negative 1 is negative 3x. Subtract 1 from the exponent, and we get negative 2. The derivative of the first times the second, 2x cubed minus 7. Plus the derivative of the second. 2 times 3 is 6x squared. And the negative 7 is a constant, so there's nothing there. Times the first. 5x to the negative 1. I'm sorry, 5x to the negative 2 plus 3x to the negative 1. And this, then, is the derivative of that product. That is the product rule. Similar to the product rule is what we're going to call the quotient rule. And I should probably label this as C. The quotient rule. It's got two tweaks to make it different, but it's very similar. If I'm taking the derivative of two things that are divided, f of x divided by g of x. Be careful, this is not f prime divided by g prime. We can't just divide the derivatives. Instead, we will take the derivative of the first times the second. And because this is division, we'll actually subtract the derivative of the second times the first. And the big difference here is we have to divide by the denominator squared, which is kind of interesting. We end up with this squared denominator in the denominator. So for example, if I'm being asked to find the derivative of 4x squared minus 5x plus 1 over x squared minus 7. We've got a top piece, and we've got a bottom piece. Keeping track of that, then, we take the derivative of the first piece. 4 times 2 is 8x minus 5 times the denominator, just like it is, x squared minus 7. Then we subtract the derivative of the denominator. X squared becomes 2x times the numerator, which is 4x squared minus 5x plus 1. And then in the denominator, we take the old denominator, x squared minus 7, and we square it to get our final big, ugly, but correct derivative. This formula takes a little bit of practice to get really comfortable with, but it certainly is much nicer than doing it with the derivative formula. Let's do another one. Let's take the derivative of the square root of x over 2x cubed minus 7 over x. One thing you might notice right away, let me buy us some whiteboard space, is that we need to rewrite that so it's that friendly polynomial so we can use our exponent trick. So we're going to actually find the derivative. Square root is really just a 1/2 power over 2x cubed minus 7x to the negative 1, which is what moved that x into the denominator. Now we have a clear numerator and denominator to use in our formula. We take the derivative of the first one, pull the exponent out front, x, subtract 1 from 1/2. 1/2 minus 1 is negative 1/2. Times the denominator, which is 2x cubed minus 7x to the negative 1. Subtract, and then we take the derivative of the denominator. 2 times 3 is 6, x squared. Negative 7 times negative 1 is positive 7, x to the now negative 2, times the first function, which is x to the 1/2. And this is all over that denominator, 2x cubed minus 7x to the negative 1 squared. And we now have the derivative of our quotient. Now that we have a couple derivative rules, we can actually take a look at some applications of the derivative and solve some more interesting problems. And one of the most common applications of the derivative is the relationship between the position of an object, the velocity of that object, and that object's acceleration. All three of these things are connected by derivatives, because the derivative is the rate of change. And so the velocity describes how the position is changing. The acceleration describes how the velocity is changing. So these three variables, or functions really, we can make for each of them. The position describes where the object is at time t. And we will use the function s of t to represent the object's position at a given moment of time. But it's moving. And so to describe the speed or rate at which it's moving, we have the velocity, which the velocity can be thought of as speed, but speed doesn't really have a direction. Velocity does have a direction, positive generally meaning to the right, negative generally meaning to the left. So speed with direction, or the rate of change at which the position is changing. So the change in position. So we will use v of t to represent the velocity at a specific point in time, but because it's the change in position, we say that it's the derivative of the position. Finally, we have the acceleration, or how fast the velocity is changing, the change in velocity. And we use a of t to represent the acceleration. And because that's describing the change in velocity, that's the derivative of the velocity, or the second derivative of the position. So knowing that we have this relationship between position, velocity, and acceleration, all connected by the derivative, we can solve problems in relationship to these three questions. So for example, if the position of an object in feet after t seconds is given by s of t is equal to t cubed divided by 5 minus 3 over t squared. What is its velocity and acceleration after 2 seconds? First thing I'm going to do with this function is I'm going to change it to be a nicer polynomial because I don't like having or a nicer rational expression. I don't like having the fraction in a fraction. So I'm going to write that as t to the negative 2. So s of t is equal to t cubed over 5 minus 3 t to the negative 2 power. And then we can take the derivative of this function to find the velocity function. So the velocity at time t, this is a quotient. So we take the derivative of the top, which is 3t squared, times the denominator, which is 5 minus 3t to the negative 2, minus the derivative of the denominator, which is negative 3 times negative 2 is positive 6t to the negative 3, times the numerator, t cubed, all over the denominator, 5 minus 3t to the negative 2 squared. I'm going to clean that up a little bit just so that we can take a second derivative of it, because we're also being asked about the acceleration. So when we distribute through, we get 3 times 5 is 15t squared minus 9. And when we add the exponents, we get 0 t's. And then minus 6, and we have 0 t's. Since we have negative 9 minus 6, I'm going to write that as negative 15. Over, and I'm going to go ahead and square this out. We've got 25 minus 30t to the negative 2 plus 9t to the negative 4. So we should be able to calculate the velocity after 2 seconds by plugging 2 into this formula. 15 times 2 squared minus 15 over 25 minus 30 times, not t, but 2 to the negative 2 plus 9t, which is 2 to the negative 4 power. And we can plug this into our handy-dandy calculator. Second quit to get me to the home screen. We need a parentheses around the numerator. 15 times 2 squared minus 15, close the parentheses, divided by parentheses for the denominator, 25 minus 30 times 2 raised to the negative 2 power, plus 9 times 2 raised to the negative 4 power, and then close the parentheses on the denominator. And my velocity at 2 seconds seems to be about 2.49 feet per second. Almost 2.5 feet every second this guy's going to travel. That's the velocity. But the problem's also asking for the acceleration. So let's scroll down to give us some more whiteboard space. The acceleration, then, at t is going to be the derivative of the velocity. So we've got this derivative of a velocity function. So we'll take the derivative of the numerator, which is 30t, times the denominator, which is 25, minus 30t to the negative 2, plus 9t to the negative 4, minus the derivative of the denominator. Negative 30 times negative 2 is positive 60t to the negative 3, minus 36t to the negative 5, times the numerator, which is 15t squared minus 15. And then that is all over the denominator squared, 25 minus 30t to the negative 2 plus 9t to the negative 4, all squared. Now the problem was asking us what's the acceleration at 2 seconds. So in order to get that, we're going to need to go back to our calculators. I'm not going to write it out. I'm just going to put 2 in for everything all the way across here. So we've got a numerator, parentheses, 30 times 2, open a parentheses, 25 minus 30 times 2 raised to the negative 2 power, plus 9 times 2 raised to the negative 4 power, close the parentheses, minus, open a parentheses, 60 times 2 raised to the negative 3 power, minus 36 times 2 raised to the negative 5 power, close the parentheses, open a parentheses, 15 times 2 squared minus 15, close the parentheses, and close the parentheses on the numerator, divided by denominator, open a parentheses, 25 minus 30t, which we know is 2, raised to the negative 2 power, plus 9 times 2 raised to the negative 4 power, close the parentheses on the denominator, and square the denominator, and hit enter to find out our acceleration is 2.44 feet per second squared. So it might have been ugly to type in the calculator, but it just took time. It wasn't difficult plugging 2 in for all those t's. So that's velocity, acceleration, and position, derivatives of each other. But the big thing that I want you to practice with these differentiation rules, specifically focus on the product rule and the quotient rule. The sooner you master those, the more advantage you will have moving forward in our calculus class. So take a look at those, practice, 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 and we will see you in class to practice some more.